بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 11 من Random Variables and Stochastic Processes. اليوم بدنا نتكلم يعني بدنا نعمل extension لل Random Variables ونتكلم عن multiple Random Variables. So today lecture is about multiple random variables. لما نتكلم عن multiple random variables عم نتكلم على more than one random variable at the same time, their density, their distribution and things like that. في نفس الوقت احنا بنحب لما نتكلم عن multiple random variables معناته احنا ممكن نتكلم من 1 إلى infinity number of random variables. لكن لما نتكلم عن multiple وفي نفس الوقت بدنا ناخذ يعني نظرة واقعية، أفضل شيء نأخذ المينيمم multiple. The minimum multiple is 2. So the minimum multiple لما نتكلم على multiple معناته the minimum multiple is 2 random variables. طبعا ليش باخذ 2؟ لأنه في نفس الوقت لما برسم مثلا البي دي اف أو برسم الديستريبيوشن السي دي اف او البي دي اف برسمهم بالثيرد دايمنشن، فبضل دائما بنتفرج عليهم نقدر نشوفهم we can visualize them. اذا صار في عندي 3 random variables والهم بي دي اف او 4 random variables لهم بي دي اف، بده يصير في عندي هون abstract math. الانتجريشن والديفرنشيشن it's applicable still but you cannot see them, you cannot visualize them. 2 random variables بتقدر ترسم ال 2 random variables x1 و x2 أو x و y in the xy plane وترسم البعد الثالث تحط فيه density أو distribution so that you can still يعني visualize them, draw them, do the integrations while you can still imagine how it looks like. So this is much easier to visualize. Okay, but this is, although this is applicable for any number of random variables. Okay, so we had in case of one random variable, we defined an event A by A is equal to x less than or equal small x. This is our event. Or another event B, or now this is y less than or equal y, and so on. Now, if when I go for multiple, then the joint event A intersection B or AB is defined as x and put a comma here, y. So the comma is representing that you are doing the joint event of x less than or equal x and y less than y. Now we can define the joint event x1 intersection x2 intersection x3 intersection x sub n to be x less than or equal x1, x1, x2 less than or equal x2, and x sub n less than or equal capital X. This is small x. Okay. Okay, let's put these notes that we had before. Notice that when we talk about multiple random variables, 2 is the minimum multiple. Okay. 2 is the minimum multiple where we can visualize it. We can visualize it. I mean, you can draw x, y, and z. So you have, this is the random variable x, this is the random variable y, and z. You can, let's say that you have fxy of x and y. The density function or the PDF function or fxy of x and y. So in the third dimension, you can see it. This is why we will concentrate on 2 random variables, because they represent multiple random variables, and at the same time you can still draw the plots of the PDF and the CDF in 3 dimensions. Okay, so I'm gonna go directly to the joint distribution function. And its properties. Okay? We had before fx of x, we said that this is equals to the probability that x less than or equals small x, and f y of y is equal to the probability that y less than or equal small y. Now I'm going to define fxy of x and y is equal to the probability of the joint x less than or equal small x and y less than or equal small y. Okay? So this is the joint distribution function of 2 random variables. Okay? You can say, okay, I can also say that this is fx1, x2 of x1 and x2 equals the probability that x1 less than or equal x1 and x2 less than or equal x2. So this is both 2 representation of the same thing, but usually when we have 2 random variables, it's much easier, or it's more convenient to use x and y instead of x1 and x2. If we extend the number of random variables, then we can say that, okay, this is fx1, x2 up to x sub n of x1, x2 up to x sub n equals to the probability that x1 less than or equal x1, x2 is less than or equal x2, and up to x capital N less than or equal x capital N. So this is the density function of 1 random variable. This is density function of joint density function of 2 random variables, this and this one. And this one is a joint distribution function of multiple random variable. Okay. Let's see how we are going to do this. If we have an example of values that we have here, x comma y, a pair of values. So you have 1 and 1, we have 2 and 1, another point, and 3 and 3. There are discrete random variable of x and y, 2 dimension, and we have the probability of x comma y is equal to 0.1, 0.3, and 0.5. So we need to find fxy of x and y, which is this definition, which is equal to fxy of x and y is equal to the probability that x less than or equal x and y less than or equal y. Okay? Now, if we start evaluating fxy from the probabilities that we have, let me first do it by drawing. So this is my variable x, this is my variable y, and this is my fxy of x and y. Okay, we have 3 values, so I'm going to draw them on the xy plane. Okay, so this is 1, 2, 3, and this is 1, 2, 3. So at 1 and 1 here, at this point, before this point for x and y, fx and y is equal to 0. We don't have any probability. At this point here, we have an 0.1 probability, and it goes in this direction, and it goes in this direction. So it will go so this is, it's like a step of 0.1 above the xy plane, starting its corner at 1 and 1, goes in this direction to infinity, goes in the other direction to infinity. So this is the 1 and 1. Okay, 2 and 1. You have 2 in the x-axis, 1 here. So this is above this one here. You have also height of 0.3. This is a height of 0.1. And this one also will go in as if you have stairs, you know. So this one also goes like this. Okay, and the last one is at 3 and 3. 3 and 3 is here. So this one will go up here like this. And this is 0.5. So this is a 3 and 3. Now if you add 0.5, 0.3, and 0.1, those are 3 steps, and those 3 steps add up here to be 1. Okay, so the whole thing is 1. So those are stairs. I'm not very good in drawing, sorry about that, but this is how you're gonna see them in 3-dimensional space. And this is our fx of x, and we can find fx of x to be fxy of x and y is equal to 0.1. I'm sorry, I think there is a mistake here, 0.5, 0.3, 0.2. So this one should be 0.2, and this one here is also should be 0.2. So this is a 0.2, it's not a 0.1. So all of them should add to 100%, which is 1.0. So this is 0.2 u of x minus, our x here is 1 times u of y minus 1 plus 0.3 u of x minus 2 u of y minus 1 plus 0.5 u of x minus 3 times u of y minus 3. Okay. Okay, so this is our okay. This is our discrete random variable, and this is how it looks graphically, and this is how we represent it mathematically. Okay. So for the discrete, multiple random variables, we can say that f x1, x2, xn of x1, x2, xn is equal a double summation from n equals 1 up to capital M, m equals 1 up to capital M, probability of xn ym u of x minus xn times u of y minus ym. So this is a general representation of the distribution function for the discrete random variable, and it looks like this. Okay. Double unit step function, one in the direction of x and the other one in the direction of y, and you have a double summation as we did here. And you notice that this one here, you have n and m. Those are the values that we have, and we represent it in this manner. Okay, so what are the properties of the joint distribution? The first property is that fxy of minus infinity and minus infinity should equal 0. You know, this is like a direct extension, but not only this one. Fxy of minus infinity and any y should also equal 0. And fxy of any x and minus infinity in y. So if you go to the minus infinity corners, from x, from y, or from both, you should start from 0. Okay, the second one, fxy of infinity and infinity should equal to 1. But fxy and y and infinity, or x and infinity, or y and infinity, they are not, they have special names. We'll see them in a while. Okay, 3, fxy of any x and any y should be a value from 0 less than 1. So those values are between 0 and 1 still. So it's normalized value of the distribution function. Property number 4, fxy of x and y is a non-decreasing function. Non-decreasing function in both x and y. It's a non-decreasing function, means that it increases or it has a constant value, but it cannot decrease. So if you have x1 and x2, and x1 is less than x2, then the function at x1, evaluated at x1, is definitely less than or equal to the function at x2. 5. fxy of x2, y2 plus fx plus fxy of x1, y1 minus fxy of x1, y2 minus fxy of x2, y1. This is equals to the probability that x is between x1, x2, and y is between y1 and y2. Okay? How to visualize this? Let me just draw the following plot in 2 dimensions and see what will happen. I'm gonna draw the xy plane. So this is my x, this is my y, and here going out of the plane is fxy of x and y. So f of x and y is going outside the whiteboard. Going out like this is the distribution function. Now I'm gonna draw a line for x1 and x2, and you have here y1 and y2. What I need here is to find what is the probability over this area, not over this area, but the probability that you will have your x is between those 2 regions. What is the probability of this and the probability of this? Okay. Now, if you evaluate fxy here, fxy of x1, x2, and y2, actually you are taking the whole area from minus infinity to x2, from minus infinity to y2. So this is, I'm gonna draw this with a red line. So this is the whole area. Okay. Now, so the first term, you are not taking this, the probability of this area, you are taking the probability for the whole area. Now, if you take this negative part, this negative part is fxy of x1 and y2. x1 and y2. So this is fxy of x1 and y2. So you are taking this area. So if you substitute negative minus this one, you end up with this strip here. Okay? Now if you take the second negative, this is the one, fxy of x2 and y1. So you end up subtracting with a minus sign you end up subtracting this area. Now, actually, we need this one. So we took the whole area, we subtracted this one, we subtracted this one. But what happened? This area here, I'm going to draw it with the blue. This area here, which has the fxy of x1 and y1, was subtracted twice, one from this one and one from this one. So you have to add it positively. This is why we add this one positive, and those two negative to give us the probability of this area here. Okay? Okay. So this is number 5. Number 6, from the properties, we have fxy of x and infinity is equals to fx of x and fxy of infinity and any y is equal to fy of y. Those two functions are called the marginal distributions. And they are also distributions. I mean, if you need to get fx of x, you substitute infinity in the distribution of the joint distribution. If you need to get the distribution of y only, then you substitute infinity for the joint distribution of those two. Okay? And here, properties 1, 2, and 5 are used to test whether some function, if some function can be a valid distribution. Valid distribution function or not. Okay? Okay, so I'm gonna just go to the previous example that we had before and get the marginals. Example, we have fxy of x and y equals 0.2, u of x minus 1, u of y minus 1, plus 0.3, u of x minus 2, u of y minus 1, plus 0.5, u of x minus 3, u of y minus 3. Okay? Find the marginal distributions fx of x and fy of y. Okay? So fx of x is equal to fxy of x and infinity. Now if you apply infinity here, the unit step of infinity is 1. So this is equals to 0.2 u of x minus 1. Also y equals infinity, so this is 0.3 u of x minus 2 plus 0.5 u of x minus 3. And fy of y equals fxy of infinity and y, and this is equals to 0.2 u of y minus 1 plus 0.3 u of y minus 1 again, plus 0.5 u of y minus 3. Now, you look at those two unit step functions, they are overlap of each other, so we can say that this is 0.5 u of y minus 1 plus 0.5 u of y minus 3. So this is our fy of y, and this is our fx of x. Okay? Okay. So this is the properties of the joint distribution. Let's move to the partner of the joint distribution, which is the joint density function. What is the joint density function and its properties? Okay? So the joint density and its properties. Okay, so the joint density function f x y of x and y, so we use lowercase letters for the density, and this is equals to the second derivative of the distribution with respect first time with x and the second time with y, or vice versa. First time with y, second time with x. It is, both are acceptable. And for the discrete case, we know that fxy of x and y equals to double summation from m equals 1 to m to n, m equals 1 to m, probability of xn ym times delta of x minus xn times delta of y minus ym. Okay? So this is the density, and we can see that for the example that we had before, so for our previous example, when we had x and y with 1 and 1, 2 and 1, and 3 and 3, we had probability of x and y equals 0.2, 0.3, 0.5. We can say that our fxy of x and y equals 0.2 delta of x minus 1 times delta of y minus 1 plus 0.3 delta of x minus 2 delta of y minus 1 plus 0.5 delta of x minus 3 times delta of y minus 3. Graphically, this looks like this. So you have here x, you have y, and the density function of x, y of x and y, and you have one, two, three, you have at 1 and 1 a delta function of 0.2, you have 2 and 1 a delta function of 0.3, and at 3 and 3 you have a delta function of 0.5. So you have 3 deltas located at the points 1 and 1, 2 and 1, and 3 and 3, with each delta, two-dimensional delta, in the xy plane, and their amplitudes are in the third dimension. And this is how they look like. So we can say that if you have multiple fx1, x2 up to x sub n of x1, x2 up to x sub n equals to partial nth derivative of fx1, x2, x sub n of x1, x2, x sub n, partial x1, partial x2, up to partial x sub n. Okay? This is the relationship of the joint density with the distribution for the nth dimension. And we can also go to the opposite, which is the integration. So to find the distribution from the density, we can say that fx1, x2 up to x sub n of x1, x2, x sub n is equal to multiple integrations from minus infinity to x1, from minus infinity to x2, from minus infinity to x sub n of f x1, x2, x sub n of z1, z2, z sub n, dx1, dx2, up to dx sub n. Okay? Okay. All right. What are the properties of the joint density? First property, the density function or the joint density function of any random variables is greater than or equal 0. Okay? So because the distribution was non-decreasing function, so the derivative is always greater than or equal to 0. Second, double integration from minus infinity to infinity, minus infinity to infinity is equal to dx dy. So before we had the area under the curve, now we have the volume under the surface. The surface fxy of x and y, two-dimensional surface. The volume under the surface should equal to 1. Property 3, fxy of x and y is equal to the double integration from minus infinity to x, from minus infinity to y, fxy of z1, z2, dx1, and dz2. This is generalization of this one. Number 4, fx of x is equal to double integration, the first one inside from minus infinity to infinity, and the second one from minus infinity to x. So you are doing the inside integration with respect to y. So this is fxy of z1 and z2, but the integration inside over z2. Okay? And the integration outside over z1. Okay? So the integration inside, you totally get rid of z2, so you end up with x, you integrate over x, and you get fx of x. Okay, now fy of y is the second pair, or is the integration from outside minus infinity to y, integration inside from minus infinity to infinity over x. So this is fxy of, but not x, z1 and z2. Now z2 is the variable outside, so this is z1, the z2. Okay. Property number 5, the probability that x is between x1 and x2. x2 is a variable, and y is between y1 is or equal y2. This is equals to the double integral from x1 up to x2, y1 up to y2, fxy of x and y, dx, dy. So the probability underneath this region is the volume underneath this underneath this surface. So this is the surface in the xy plane. Underneath this region you have this probability. Okay. Property number 6. You have fx of x is equal to the integration from minus infinity to infinity fx of xy of x and y over dy. So that when you integrate the density over from minus infinity to infinity, you get fx of x. Okay, and it's also equals to d fx of x by dx, and fy of y is equal to the integration from minus infinity to infinity fxy of x and y dx. It also equals fd fy of y by dy. Okay. Now we can use property 1 and 2 to make sure that any function is a valid density or joint density function. So property 1 and 2 so properties 1 and 2 may be used as sufficient test to determine if some function can be a valid density function. Okay. Let's take an example. Let fxy of x and y equals to u of x, u of y, x e to the minus x times y plus 1. So this is a two-dimensional and it's in the first quadrant في المربع الأول، لأنه هذا مضروبة u of x and u of y، يعني x موجبة y موجبة، فأنت في المربع الأول x e to the minus x times y plus 1. This is the joint density. والمطلوب find the marginals, this marginal densities f x of x and f y of y and f y of y. Okay, so to find fx of x, we have to integrate from minus infinity to infinity, but because you have you are integrating over y, so y goes from 0 to infinity, so this is from 0 to infinity, u of x times x e to the minus x y plus 1 times dy. So this is equals to u of x times x e to the minus x. We take it outside, so you have e to the minus x y dy from 0 to infinity. So this is equals to u of x times e to the minus x times the derivative of this one is e to the minus x y over minus x, and this is from 0 to infinity. And if you apply infinity, this is 0. If you apply 0, it's 1 with a minus sign, and you have two minuses. So u of x times x e to the minus x times 1 over x. So this one will cancel, and you have u of x e to the minus x. This is an exponential PDF. Exponential PDF, and this is fx of x. Okay. To do fy of y, so fy of y is equal to the integration also from 0 to infinity over x, because you have u of x here, so you have u of y times x times e to the minus x y plus 1 dx. So every y here is a constant, so you have u of y times the integration from 0 to infinity x e to the minus x times y plus 1 dx. So we do it by parts. We have to let u equals x, dv equals to e to the minus x times y plus 1 dx. If you integrate this, you have minus e to the minus x y plus 1 over y plus 1. The differentiation of this one, du equals dx. So we multiply, and here we have minus integration. So you have u of y times, the first one is minus x e to the minus x y plus 1 over y plus 1 plus the integration from 0 to infinity e to the minus x times y plus 1 over y plus 1 dx. And we have to integrate the second term. Now the second term has only the exponential, so it's straightforward. Okay, so we'll have u of y times minus x e to the minus x times y plus 1 over y plus 1, okay, minus e to the minus x y plus 1 over y plus 1 squared. This is from 0 to infinity. Now, if you apply infinity, you have infinity here 0, and you have here 0. So the term is 0, so you have u of y times 0 minus, and you have a minus sign. The first one when you apply 0 for x, so this x is 0. The second term you have minus, minus, so it's plus. So inside here is minus 1 over y plus 1 squared. So you have the function is u of y over y plus 1 squared. So this is f y of y, which is the marginal density of y, the marginal density of y. So those are the properties of the distribution, the properties of the density function. We will continue in next lecture about some more issues on multiple random variables, such as the independency and consequences of those. What is the consequences of the independency, the correlation, the autocorrelation, the cross correlation, and all those moments that related to multiple random variables. Thank you very much for being with me in this lecture, and we will see you in the next one.